Alrighty. Let's bust open the. Hey! 1 minute ahead of schedule here. This morning's been pretty hectic for me. I got delayed a bunch, but seems like I got done with everything in time after hustling some. So let's go ahead and put a check on this because I did make it on time. Alright, save this event. Come on. Alright, what's the game plan? Well, I need to finish my lab. Let's go ahead and read over part B. So where we left off on the labs, if I just open up trans.c, which has a totally different meaning nowadays than when they probably wrote it, but it's a matrix transpose. So I wrote these print matrix and minimax helper functions. These could be pound defines, but whatever. And then this is my actually the solution that I'm working on. So it iterates over in batches, and the batch size is determined by this divisor or dividend. What is the difference? In division, what are the names of the operands? I call this a divisor, but it might be a dividend. I think it's divisor. Come on, AI. And OpenAI is just like slacking. Well, and you want to be, oh, there we go. Divisor. Okay, that was right. Cool. So divisor and dividend. Okay. So I was right. It was divisor. And then we reiterate over every element of that batch. The batch sizes, we could control them using these batch components. And all of that works correctly. I could pull these things out, these pound defines out, and put them up here. Because they're global to the file. But why do that? Why not just put them there because they're most relevant to this algorithm here. Can you define consts? Can I say something like const foo is equal to 5? What are you doing? Come on. Const foo is equal to 5. A type system is required for all declarations. Constant. Okay, why don't we do that instead of a pound define? Const int, make these both constants. And then we can do a little code rename. Batch component. Code rename min batch size. There we go. That way they're local to the function. Okay. Cool. Oh, I did need to go down here and implement the things that are not on the batch size boundary. But let's see if that's even required. The evaluations for B. Let's go to there. Their powers of no, one is 61 by 67, so it is an odd number. So we need to implement that. Let's go ahead and just do that. So what does this represent? So we're going over A batch rows. So each one of these is a row of batches. And if we go over here and actually run it, so I'm going to jump back to This would be under what? Cache lab. And we want to run our transgen, I think it is. What is it called? Yeah, tracegen. You have to get some flags here. It's funny that it cores dumped out the flags. It's like, okay, these guys didn't really give a shit about protecting that. This is the thing that actually runs the program. So tracegen. I forget the flags. Do we not have this? Trace. There you go. Okay, let's do it on 3 by 3. And I want to print out the batches as we should be printing them out. So the min batch size is 2, so that doesn't really work. We need something like 5 by 5. So we stay on row 0 and then we go to row 1. So we're doing row 0, row 0, row 1, row 1. And then we got at the end of the batch. So here, at the end of this, so this is handling the rows. So at this point, all batches for the row have completed. At this point, all rows have been completed. So in here, right at the end of the row, what we need to do is see how many we have left. We have to do a two-dimensional, potentially two-dimensional batch, an additional batch at the end. And to get to two-dimensional, we're going to need a size of 3. So it'd be 3 times 12 plus 1, roughly. Or we're going to do plus 2 to get this to really show. So 3 times 4 plus 2 is 12 plus 2, 14. So the n would be 14. No. M is rows. And then we invert it there. Okay. Okay, so we had 4 different batches of size we should print out the A batch rows and A batch calls. Make. Alright, so our batch size is 2 by 3. And we have 4 of them. And they're of size 3. Okay. And then you have 2 remaining. So this should be a simple computation here, simple arithmetic, where we say, okay, say take A batch rows, multiply that times the number of batches. Wait a minute, A batch rows. No, it's gonna be calls. Multiply it by the number of batches. Which would be m divided by that times that. So we just want m. So what is this value? This is, we want mod here. Mod. I guess the remainder. Remaining calls. Yeah, we can compute these out here. And then we'll do here. Okay. Sorry, no A. Let's go ahead and make. Oops, make. So we should have one remaining row and two remaining calls. Yeah. Okay, so here at the end of every loop here, we gotta say for every call, auto. So we're doing ij inside there. Let's just do auto at o is equal to 0. O is less than something, and then it's gonna be O plus plus, and then we do the same thing P here. P. So we'll say transpose rem. Really, this is going to be a KL type deal. So let's do K and L, K and L, K and L. We'll do this inside here. What is this saying? Expected expression. For auto K is equal to 0. K is less, I need to fill this in. Let's say 0 for now. So inside here, we need to, I'm going to print off debugging here. And we don't need that. Pretty much you want to do the same loop here. So I'm just grab this whole freaking loop here. Just paste it in here. Is that correct? Yeah. Wait a minute, why is this print matrix? That doesn't seem right. I think we're missing that. There we go. I think we need to be up here, right? So in here we have all of our rows completed. Once we're done with that, so we're gonna need to do some more. Here, at the end of this loop, no, this actually does belong up here. So at the end of this loop, we have all of the columns inside the row completed. Batch for this row. Row %d, and I'm gonna just pass that in here as I. No, it's not I. It's going to be I times batch rows plus K. No. We can't determine the row here because we're still in batch mode here. So doing the remaining batch, it would be nice to know where we're at though. Like what batch is it? I think it would be worthwhile computing that. So the batch would be I times the batch size. Yeah. And then this would just be do we know the column? We should know the column, right? Oh. I'm getting confused again. I need a better diagram. Well, I need a diagram. So M in A represents a number of columns. M is number of columns. So when we called here, we're looking at A. So N is the number of rows and M is the number of columns. N, M. N is the number of rows. This is going to be N over here. and then this is going to be M up here. And we're iterating through n divided by a batch number of rows. So n would be here divided by the batch number of rows will give us a max, and we're going iterating through that. So I is our rows, our batch 0th row. So we can rely on I. So I is literally there. And then if we want to figure out where we're at M, it would be M times, or M divided by a batch calls would be where we're at N in calls. So let's do that, and we'll comment out the loop because obviously that's not, the loop's not complete. I want to see what, if I make this, oops, go back up here. So we get it down here, and then we have a remaining batch 0, 4. That's right. And then remaining batch 1, 4. That is correct. And I want to make the batch size a little bit bigger, because right now it's one row. Sorry. We have 2 columns at the end, and we have. But if I increase that at all, the batch size would need to increase as well. Let's go ahead and do like 14. And then I want to get 3 down at the bottom. To get 3 down at the bottom, that means our batch size has to be 4 rows, which means that 4 times 4 would be 16 plus 3 would be 19. So it needs to be 19. And so that gives us a size of, a batch size of 4 rows by 3 columns. And then the remaining rows are going to be 3 and the remaining columns are going to be 2. So 1 off of the batch size. And if we go through here, so we're at batch 0, 0, we're going to be handling the columns first. So we handle 3 of those. Sorry, we're going to handle the columns. How do we get to 0, 3 if... Oh, sorry, the column, it's the size of the column, not the number. So each one of these has 4, basically. So we do all 4 of those, and then we have remaining batch 0, 4. And then we go 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, yeah. Should be 2, 4, yeah. 3, 4. And then down here, we're going to have a remaining rows. Oops. And it's going to be the number of rows remaining, which should be n divided by a batch rows. And then this will be the same. No, this will be 0. So hit make on that, go back here, look at this thing. Remaining rows. So we were at batch 3, so we did 3. So we did 4 batches of rows, and now we're on the 5th batch. Okay. Let's go ahead and do the transpose then. And down here we can see our correctness is wrong, because expected a certain value got a different value. So here, we need to iterate over that one batch. So K is going to start at I times the column size, right? Or do we want to iterate over rows first? Okay, I can start at, or K can start at I. Or we can just do 0. So K is 0. K is less than the row, yeah. K plus plus, okay. And then we say, hey, take your batch rows, multiply it times I, which is the right value. Because when we got through here, we're still in the right row, yeah. And then we do plus K, yeah, that's all great. A row becomes B column, so that's all great. And then we're gonna do L, so now we're doing through columns, and we say, this is where we have to advance. So we set L to 0, L is less than the column width, that's right. And then we compute the column here, where we say, hey, columns times J. Well, J is not defined, bro. We need to define J here. So it's going to be equal to M. I mean, I hate to do it, but it's M minus the remainder. It'd be divided by and then multiplied by this. And you might think, like, okay, well, those counteract each other, but they're integer divisions. I'm thinking about a way of doing it without dividing and multiplying, though, because it seems kind of silly. It'd be M divided by A batch columns times A batch columns. Because doing the division gives you integer division, and then multiply it out. And I don't want to do the multiply anyways, so M, I'm trying to think here. N minus the M mod of it would also work. But I kind of like the division. So auto remaining call position M divided by A batch calls. That gives us how many batches have already been completed. Then we need to multiply it times A batch calls. And then we need to say, hey, that plus remaining call position gives you back a call. Yeah. Okay. Let's see if that works for handling the remaining batch. So let's go to the beginning here. So we're at 0, 0. We have remaining batch 0, 4. And we don't perform any moves? That's weird. That is very weird. Okay. L. Let's go up here. So we got our KLs now. Okay. So remaining dash did do moves. I guess maybe I didn't compile it correctly. So let's make it again. Alright, let's go back up here. So we have a remaining batch. And then here we're doing individual position moves, yeah. And this is going to be, if we go up here, just want to visualize this appropriately. So remaining rows is 3, remaining calls is 2. So this is the size of remaining calls is 2, remaining rows is 3. If I do a copy here, so remaining calls is going to be 2. And the size of the individual column is 4 rows by 3 columns. So it's 4 rows. Yeah. So this is the thing that we have at the end here. And then the remaining rows will be 3 long, or 3 high. And they'll be insanely long. We'll just do okay, so this is what it looks like at the end of the array here. Little clusters of these followed by a bunch of rows. So if we go back over to this trace here of the remaining batch, so we're going over each row first, 12, 13, 14, yeah, it looks right. Yep. And then let's go to the next remaining batch. So it's going to be 12, 13, 14. Yep, looks correct. All right, so that looks correct. Then we go down here and say transpose remaining rows. Compile remaining row. I don't know why. Compile. And here we just need to iterate over each row and each column in the row. And we don't, I guess we could do it by batches. I feel like if it's just remaining for correctness, let's just do it a regular loop. So that would be literally this loop here. I and J, except I'm going to do auto here, auto, N and M. That's going to need a change. I don't know why I copied this, to be honest. All right, moving. There we go. So we need to find a row. A row is going to be equal to I, and B column is equal to a row. And then a call is going to be equal to J, And this will be B row is equal to A call. There we go. Okay, so now we got to auto all these, right? Auto them. And then we obviously can't do I is less than N. We'd say I is equal to, what's the first remaining row? If you go back over to here, M is the width. So that's appropriate for the column. But I less than N is appropriate for N condition, but we got to set I to the right location, which would be how many batches, which would be A. Now this is how many rows per batch, A batch rows. So we're doing a similar calculation to here, where we have to do remaining call position. We're going to say remaining row position, where we say N divided by A batch rows times A batch rows. And then this will be I, we'll just set that to remaining row position. So that's just being added to L each time. So you could just initialize it like we do. So pull this thing out here, say, hey, you just go there. And the column is L. And we come in, yep. Okay, I think that should be the correct algorithm. So it should pass this test. No, it didn't. Okay, let's do our initialization for both. Okay. These are getting to 3. So I think we need to start our row thing here to be 3D. Make. There we go. So 12. It looks like 13 and 14 didn't get transposed, but the remaining rows did. So I might have fucked up something when I did that transformation. I shouldn't have done that. What is all this? Oh, that's that. So down here we have remaining batch 04, and then we skip to batch. Yeah. Did not do any moves. So that means I messed up the handling here. Yeah, that makes sense. I just messed up the condition here. This needs to be M. L is less than M because you do L is, oh no, L is less than N? No, it should be M. Yeah. Just like we did less than N here. Alright, so that should be correct. Look at that. Beautiful. Alright. So here, there we go. All right, so it's correct now. So get status, get et al, get DC. Here we say initialize input array to sequential values and output array to all -1 for easier debugging. All right, get et al, get DC. Those are just renames, some printing. I think that's how you spell matrices. 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 M-A-T-C-E-S. M-A-T-R-I-C-E-S. Matrices. Okay. Cool. So now if I run my test trans, isn't there like a, let's go back to, they don't say which program it is. All right, working on part B. We have provided you with an auto-grading program called testtrans.c. That tests the correctness and performance of each of the transpose functions that you've registered with AutoGrader. You can register up to 100 versions of the transpose function in a trans.c file. Each transpose version has the following form. All right, driver.py. Okay, we need to run this in the container. Docker run network none, all that shit. Okay. do another make inside here. Okay, the GCC is old, so we'll do, instead of 23, we'll do 2x. Alright, let's get out of here. So why was the driver not working here? Because it's running in Python 3 versus Python 2. Can I install Python 2? Python 2? Doesn't look like it. I wouldn't think Arch would make that available. So I do need to run it inside Docker just with a newer version of GCC. Can I do something like apt get update sudo? Oh, I don't have network on this thing. So I do need to get my network going here. Can I rebuild the Docker? Just have network during the build stage? Nope, that's not what I wanted. I want to do Control B this, and then, or actually, can I do bash up here? Yeah. Can I go back to labs and say, oh, they already built the Docker container. Okay. Can't do that, so let's run it without network. Fine, it's fine. Sudo apt get update. Sudo apt get upgrade GCC. Yes. Come on, why does this take so long? Alright, so now I can run make cd dash, sorry, cd home make. How is that still possible? That you don't have an up-to-date cat etsy lsb release? I guess it's 2020, that's why. Okie dokie. So I have to make it inside of here. Or I could try getting a Python 2 version running. Yeah, different Docker container. I think what I might have to do is just say auto. I think auto should be int everywhere I used it, right? Yeah, it's int anyways. Pound define auto to be int, and we're done. Alright, so now I can make. Let's hit Control D on that, rerun it. CD home, vim, make file. Go down to here, make this 2x for now, and make. ignoring return value of... Well, that's not my fucking program. That's the classes, the instructors. So how about we don't warn on that? We'll just say W error. You can warn, but I'm not gonna. There we go. Set tech OVI. Let's go back here. Make everything good. Okay, so now we can run our driver. Pi. Okay, it still doesn't like it. But to see some stuff I don't care about, I just want to run the trans stuff. And I'm curious if mine beats the my over-engineered solution of batching, if that actually beats the default simple solution. Doesn't seem like it. Seems like it's taking forever. Alright, let's jump over to our trans. Oh, I got 0 points. Nice. I'm not doing too well here. Okay, so what we're gonna do is we're just gonna copy this whole thing and paste it in here. And call this guy trans submit, and then just call this something other temp. So these were the results here, about 326,000 misses and 81,000 on the other array. 326 and 81,000. So I'm going to remake. We'll rerun this. So yeah, theirs is way better. But mine's correct. It correctly is way less optimal. Okay, it's always the inner loop that's a problem. Maybe it's this printf, all the fucking printfing that I'm doing. So let's pound to find out the printf debug. I forgot to disable that. And I think that makes it to where it's nothing. Just goes away. And then let's go ahead and comment this out and rename this back to this. Make 77. What was I complaining about? Remaining calls? Oh, because these things are just like, yeah, no longer needed. Which means you probably should just inline them. Yeah, let's do that. Okay. Alright, now we do a make driver. Hopefully we can do a little bit better than the catastrophe that we saw before. Yeah, okay. We got some points now. So mine is better. It was just all the printf debugging that I left in. That makes you feel better. Okay, so my max points are 27 or 53 and I got 16. So I'm doing reasonably better. I guess the 64 by 64 I didn't do well on. Because I had 4,000 misses. Wow. But I am substantially improving upon the other algorithm. So let's put their algorithm back in and test it. Alright, and we'll just call this other for temp. Bam. Okay, let's do a make. So I did 304,000, 2,000. Let's see what they do. So I did improve substantially upon their solution using batching. I think what I need to do now is make the batching variable and possibly even batch the remaining rows. We'll say to do batch remaining rows to have better cache performance. What else can we do? Trying to think. So the main lever I have here is with the batch components and the min batch size. So I can make this higher or lower. Let's do batch components 2. Three, 4, 2,000. So it's demonstrably worse. So let's make it 8. So 3, 4, 2,000. That's worse. Interesting. I guess I had the right constant there. Let's watch the recitation again. Learn log. No. CSAPP. Oh, not that one. CSAPP there. Videos. Cache Lab.
Okay. Vict whatever is the most recently used. Should access this address, access that address, write to this address, write to that.
Let's just go to part B.
Let's see. Okay. What else? Please, for how this works. How we have a bunch, or you might, as we go through them, it's going to look them up. How we want it to become memory at runtime with malloc. And remember the warnings we gave last week about freeing everything you use and initializing memory before you use it and such. So then, after you have implemented this great cache simulator, you're going to use it to test out how efficient you can write matrix transpose. So of course, matrix transpose is the very simple problem of we have a matrix and it's got stuff in it, A, B, C, D, and we want to transpose it. So that means we want it to become A, B, C, D. So essentially, we're sort of mirroring it over the diagonal. Rows and columns are flipping. So of course, we want to be able to implement this fast because fast is better, right? How do we optimize this so that it has good cache behavior? Because now that we know about how things are looked up in the cache, this is a bunch of values stored in memory, and as we go through them, it's going to look them up. How do we make it so that we can optimize the number of times we go to look up, say we want to look up this 10, we want it to be there in the cache, if it's possible for it to be there. We don't want it to have been evicted by something else. So here we're supposing that our block size over here is 8 bytes. And these are 4-byte integers. And so we access 0, 0. This 1 is a miss. Nothing's in our cache yet. It's the first access. Okay, so then we access B0, 0 because we're moving A0, 0 to B0, 0. It's the first step of the transpose. It's a miss because we haven't accessed this address yet either. Now we're going to access A0, 1. So we get this 2. And that's a hit because we had already loaded this up into the cache. This is a block of our cache here because it's 8 bytes, so it can fit 2 of these things. We loaded it up. When we loaded the 1, it loaded the 2 with it. And then we go and we put it over here. So we put B10, we set it to 2. And this is a different block of the cache than the 1 was in, because the 2 is not adjacent to the 1 in memory, because now this is the transposed matrix. So since the memory is stored by the rows, this isn't adjacent anymore. So now that's a different block. So what should we do next? The question is, should we load up 3 and 4, or should we load up 5 and 6? Does anyone have an idea as to which would be better?
5 and 6.
5 and 6. So why should we load 5 and 6? That's right.
So in matrix, 5 and 6 will end up in the already loaded blocks.
Right, yeah. So our naive algorithm, like if we were doing transpose by hand, we'd probably just go on to 3 and 4 next, because we're just going to go across all the rows and put them in the columns. But our cache, the way it's implemented is we've already loaded up these cache blocks, the 1 for 1 and 2. And these cache blocks are going to be the ones that contain 5 and 6 in our transpose. 5 is going to go here next to the 1, and 6 is going to go next to the 2. So if we do 5 and 6 next, what that means is if these are already loaded, we won't have a miss when we go to put them in the cache, when we go to write them to matrix B. And that's good. If we go on to 3 and 4, well, then we're going to be loading up more stuff down here. And if we evict one of these before we come back around to 5 and 6, we have to load them for the 1, and then we have to load them again for the 5. And that means we did a load for each of these. If we can get away with only loading it once and filling it up with the stuff that's going to be in it before we evict it with something else, then we've improved our cache performance, and that's going to make our program run faster. Does that make sense? So this, what we've done is we've done what's called blocking. We're transposing 1, 2, 5, 6 first, and then maybe we'll do 3, 4, 7, 8, and then 9, 10, 13, 14, 11, 12, 15, 16. We've sort of divided our matrix into blocks, and we're considering it one block at a time. Because if we look at what's happening to the caches, we see that improves cache performance. So, that right here, that's where it says blocking. We're dividing into submatrices. And the best submatrix size is going to depend on the details of your cache, and it's going to depend on the details of your matrix.
So the 1, 2, 5, 6, that worked really well, but if you were to block over the 3, 4, 7, 8, and if you were transposing it, would that still?
Okay, so let's think about what blocks these are going to be in. So 3, 4. So 3, 4 is going to be another block right here together. These are two adjacent things. And 7, 8 are going to be a different block that are right next to each other. In our matrix, in our transpose matrix, these are going to end up down here as 3 here, 4 down below it, and then 7 here and 8 below it. So we'll end up with the same thing where if we miss when we load up for the 3 and 7, or the 3 and the 4 in B, but then those 2 spots are there for us to put in the 4 and the 8. Does that make sense? Okay. And depending on how quickly these things will be evicted, and how many bytes we have in our cache block, we might be able to increase the block size and get better performance from that. If this was more than 2, then maybe we'd want to consider something bigger than a 2 by 2. So this is one of the strategies that will be very helpful for you in Part B of Cache Lab. So we have an example where we're doing it here. Did you see this one in class of matrix multiplication with blocking? Okay. Did everyone? How did you feel about it? Did you understand it? Was it confusing? Confusing? Okay. Let's definitely go through it again then. So the way you multiply a matrix, 2 matrices, is that the value at index ij of the product is all of the things in row I of the first matrix multiplied by the things in J of the second matrix. You do the dot product of row I and column J to get element ij of the product. So we want to make this faster. So we're assuming here that we're in column J. As we go through them, it's going to look to be first. And then so if we do 5 and 6, it's big enough to hold 8 of these. Filling it up with the stuff that's going to be in it before we evict it with something else, then we have, and it's going to another down here. Did you understand it? Was it confusing? Confusing?
Okay, this is multiply n by n matrices and A and B. So A and B are passing just as double pointers. And we have a C, which is the result. And then we have int n, which is the width and height. And so we iterate over it in both dimensions, I and j. And then k. What is k here? K is being added and multiplied here. So the ith row we add on a k. And the bth okay. These are both row axes though, right? No, because we're doing multiplication here. So k times n will give us a stride of, in B, the row? So so we're going individual rows and we're adding on the column. So we're iterating over rows in both of these scenarios. But here we're saying, hey, In B, we're going to compute a specific offset into the row for every value n in every value k. And this one's going to be n times I plus k. Ah, shit. I can't visualize this. I'm having a hard time visualizing this. So our main iteration is the row iteration. I is going to be a row iteration. J is going to be column iteration. So for every row, say we're at I2, we're going to be iterating over all the columns. And then we also iterate again for each position in that row. We're going to iterate over all the elements in a third dimension. And then here, we're going to say, hey, the row plus the column, we're going to add, okay, so here's where we do the add. Okay, so this is effectively doing the dot product. From here, these last two lines here are doing a dot product for that C, where we already figured out our position, our ith row and our J column, and we're just adding. So doing this entire J, we're scanning over J, and we're adding on to C here. So that's a matrix multiplication versus what we're doing, which is transpose, which is arguably a lot easier.
Let me go through it again then. So the way you multiply a matrix, two matrices, is that the value at index ij of the product is all of the things in row I of the first matrix multiplied by the things in J of the second matrix. You do the dot product of row I and column J to get element ij of the product. So we want to make this faster. So we're assuming here that we're multiplying matrices of doubles, so they're 8 bytes. And we're saying that the cache block is big enough to hold 8 of these. And then the cache is going to be much smaller than the matrices. We're going to assume that it's going to just overwrite stuff. We don't have nearly enough space to just load the whole thing up. So the first iteration, we want to know, how many misses are we going to get when we calculate this. So what we do, so we have this line of matrix A, the first row. And so every time we load up the first one, our cache block is 8 doubles, so that's going to load up the first 8 things in this row. And then when we get to the 9th thing, we miss again, but it loads up the next 8. And then when we get to the 17th thing, it misses again, but it loads up the next 8. So in order to load up this row, we're going to have n over 8 misses. Does that make sense? Or n is the length of the row. Because each first member of each group of 8 is a miss, and then it loads up the rest, so they're there when we go to access them. And then when we go to do this column, well now, since we load up the first 8 of this row, when we load up the first element, the element in this corner, then that's a miss. And then we come down to the next one, and it's not there. It's not there. Our matrix is much wider than 8. So what we end up doing is we miss every single time we access the first element of that row. So every single element of this column is a miss, so that's n more misses to give us 9n divided by 8 misses total. Does that make sense so far? I would calculate that. And so then afterwards in the cache, what do we have loaded up? We have the last 8 elements of the first matrix are in our cache. And we have this 8 by 8 block from these 8 rows that we loaded up, and then the stuff over here that we didn't use, going 8 wide. So does everyone see how we get that in our cache when we're done? No? No, so, okay, so, the assumption we're making here, of course, is that our cache is much smaller, so things are being overwritten. If we had a huge cache, then maybe, all of this could still be in it. But we're assuming that our cache is just going to keep overwriting. The best we can do, if we have a really bad cache, is that this would be in there, and these 8 would be in there. Okay, so then we go again. We go again, and what happens? We do the same thing to the first row, and if we've overwritten the beginning of it, then we have to load that up again, and we load it up again, and we load it up again. And we're going to have n over 8 misses again, because we evicted the beginning of this first row. And then, once we start loading these up again, eventually we'll evict the end. And so then we have to load it up again too. And so we're going to have n over 8 misses again. And then we do the same thing over here. We have a miss every single time we access a new row. And in doing that, we're evicting this bottom block. And so by the time we come back down to it, it's been evicted, and we have to load it up again. And then we end up with n over 8 plus n misses again. Because we essentially threw away all of this stuff before we used it. And we threw away this before we used it again. And so, we look, we're going to do this n squared times, because there's n squared things in our matrix. And that's going to give us 9 over 8 times n cubed misses, which is polynomial, but this isn't an algorithms class, so that's not good enough. So the solution is we want to block it up. So we want to sort of say, if we look at just a block in C, then it's sort of that block carried across the rows and that block carried across the columns of A and B, and we can get those into C. Actually, I'm not sure what this plus C is doing here. Is that right? Because that's what we're calculating. I don't think this is supposed to be here, unless someone else sees why. So what?
Something you're asking on.
So C is what we're trying to calculate. We're trying to calculate C as the product of A and B.
Yeah,
So
page 17.
yeah. Okay. So yeah, the idea is that we're taking these blocks in the rows of A and the blocks as the columns of J. And what we're going to do is we're going to calculate the product of everything in a block before we move on and calculate the next block. So afterwards in the cache, let's see. So we're going to load up this whole first block here. We get our block size we're using is capital B. So there's n over B blocks total. What we're going to do is we're going to go through the rows, and each row of 8 we're good with. It's been loaded up already when we're going through the rows. And we've got b squared of these elements, so b squared over 8 misses to get these. And then over here, let's see, what are we doing? So we get 2n we're assuming that 3 blocks fit into the cache. Okay. So 3 blocks fit into the cache. So that's enough. That's enough for the block from C, the block from B, and the block A, and the block from B. That's good. So let's see. So over here, we are doing 2n over B times b squared over 8. See, so b squared over 8 is loading up all of the lines like before. And then the 2n over b would be, that's the number of blocks we have. Right, yeah. So b squared over 8 is the number of misses we need to load up one block, right? Because there's b squared things in it and it loads up in lines of 8. And then we get everything in that line. We use it. And then we have a block for all of them. We can play or back. How many blocks we do total, that's n over going to be better in terms of cache performance. So does this make sense? It's about locality. way and then come back to them later, we end up with better performance. It mattered that we wrote the program well. This isn't something that we got for free. We didn't get this more efficient. And you have these 3 different sizes of matrices that you have to transpose. We wrote the program well. This isn't something that we got for free. We didn't get this more efficient way of doing it unless we actually thought about cache performance when we wrote the program. So for part B, you'll get particular cache specified here, and you have these 3 different sizes of matrices that you have to transpose. You should go through the same reasoning of figuring out how the best way to traverse these matrices are, so that you block them up, whatever other strategies you have to get good cache performance. Watch out for warnings when you're compiling your code. They're treated as errors. Think about the eviction policy of the cache. That matters. It's least recently used. You'll have strict compilation flags on. That's why warnings are errors. That's the way we're going to compile it. So make sure you code with good style, because if you won't, the compiler might actually not let you compile it. Let's see. Yeah, here's man through git opt. Showed you that already. Eviction policies of cache. So these slides will be online. I know we're over time. These slides will be online, but you should know that the first row of matrix A is going to evict the first row of matrix B. They conflict with each other. They're going to, they have the same set and tag. So they're going to overwrite each other, so you need to worry about, accessing them in an order so that you don't overwrite things more than you have to. Matrices are stored in row major order, so all the elements of a row are consecutive, and then the next row, and then the next row. Read the style guideline. Any questions? Yes?
I use getline. For some reason, the shark machine is an older version of glibc and requires us to define the GNU source at the top of our file. Is that acceptable, or is that, should we just use fgets instead?
What would you be using this for?
Just to read out to grab lines from the input file.
Grab lines from the input file. You should be able to just do that with, I think we had it over here. I don't know if you need either of those. Just sort of this pattern.
Okay. I have to work with that, but I can adapt it to
Yeah. I mean, if, the source would be, if you submit it to Autolab and Autolab complains about it, then whatever you did is not good.
All right.
That's sort of the most definitive way of knowing.
So what I noticed here is that all of this is self-contained, so I can just add my own batch rows and batch columns and experiment with those. So I think what I'm getting out of here is that the 32 was most optimal for all situations, and that's why this is performing better than this, because this gets rounded to 32. So the size that we want would be 32 divided by 4, which would be what? 32 divided by 4, 8. So an 8 by 8 batch seems to be an optimal size here. So I'm just going to redefine these so we can comment these out. We'll say auto a batch rows is equal to 8, and batch calls is equal to 8 as well. Let's see how well that performs on these different matrices. So we'll go back and make this and run the driver. So now it's constant for all of them. So my hope is to get 64 down. No. Did not get 64 down, even though it's constant. What if I just did like an exit 1 here? I want to make sure this thing's compiling. So I would have expected that to have some effect on it. Like it should be 4 times as worse as, so it should be 1200 or something like that. But it's not. Okay, so invalid. Let's go ahead and delete that. Make and driver.py. So we'll experiment with some different parameters here. So that gets you 300. If we go down to like 6 here, So 343. It's worse for 6. Let's try 4. Four is better. Try the 16 here. Oops. 343 is the best on 32. Ooh, that's a lot worse. Maybe do 12. Nope. 10. Get the feeling that 8 is going to perform the best on all these. So 4 7 2 2, 4 8 2 3, 4 7 2 2. Seven 2. Oh, what was that? That got 64-bit down. So this is the most optimal for here we can say if m is equal to 32 and n is equal to 32, then we're good to do 8 by 8. Otherwise, why is auto? Because auto is pound defined up here. All right. So if I do something silly like maybe 4 here, that should change the other two, but not the first one. So 343. Look at that. Else 64. Oops. And 64. Then we do 4 by 4. Else what if I did like a 2 by 2 here? So that'd be 2 5. I think I was at 2 at 8, right? That's way worse. Can I do 16? Seems the smaller it is, though. The smaller the matrices dimensions, the bigger the batch size should be. Okay, that's 2000. If we do 2000, let me say 8 here, 8 here. So 16 was good. Yeah. Let's go ahead and copy this here. Put that there. This is not gonna be what? We'll just leave it out. Okay. We're still not doing incredibly well. What I am noticing though is that the performance of this one, which is the odd shaped one, is the worst out of all of them, which means that we could probably improve this here. The 64 by 64, 1891. Yeah, it's consistently getting 1891. Let's try 16 by 8. Just like altering it a little bit. 1891. Same thing. 8 by 8? Oh no, I did it wrong. We're in 64 land, so maybe we can do like an 8 by 4 here. Eight by 4. So we were at 1891. We're just gonna optimize 64 here. 1891. 1843. Still 1843. So 8 by 4. What if I did 4 by 8? Wow, what a big difference. 8 by 2. Eight by 8. Sixteen by 8. Why is everything messed up now? 8 by 4. I think 1891 was my best result. $18.43, okay. This one, 32, 343. See if we can get that down. 343. Nope, it's not an improvement. Do like 16. Still 343. 32. Or maybe? Nope. So 8x8 seems to be the best size there. And then for the last one, which is uneven, 2037. Let's try 16x4. $20.37. Hey, 16x4 did really well. What about 32x4? Nope. What about 32x2? So 16x4 seems to be the best so far. Nope. This is 16x4. Seems like this is the best I can do with this implementation without doing more optimizations. I'm done with this. I could optimize this more. I could implement the batching of the remaining rows. I could... What else could I do? Yeah, I could do a bunch of stuff, but I just want to finish this. Vim info get diff makefile. What was the diffs here? I don't want those. Get checkout makefile. Get status. Get all. Get DC. Pound define auto end. So we'll delete that. Make. Yep, everything still builds. And okay, I'm done here. Cool, cool, cool. Alright, kill that. And that. And that. And that, we're done with that. So where are we at? Jump over to CSAPP, vim up readme. There we go. I think we were reading chapter 8, exceptional control flow, and watching the lectures. Yeah, Yeah, I got some amount of progress in the lectures. Let's check out the exam review. Exam review. Here we go.
In case the mic didn't pick it up before, this week's recitation is midterm review because this week is your midterm. Hopefully you all know that. So today we're just going to go over some review. We're going to go over the logistics for the midterm, and then we're going to go over some review problems. And I have a few sample ones here in the slides, but I would like, if you have particular questions that you'd like to go over those first, and then we'll use the ones in the slides if you run out of questions. So a couple logistics. The midterm will be from Tuesday to Friday of this week. The midterm is designed to take 80 minutes. It's designed to be something that would have been possible to take during just a normal class period if we were offering it during class, but we are giving you up to 4 hours to take it. So you have 4 hours from the time that your slot starts to finish the midterm. So time shouldn't be an issue if you are properly prepared. If you have not signed up for a slot online, you should do so now. Professor O'Halloran sent out an email to everyone about signups for the midterm. Make sure you sign up for a slot, because when you show up, you will only be allowed to take it during your slot. Don't try showing up at a time that's not your assigned slot, because we will not let you take it then. If you forget when your slot is, you can go back to that website where you signed up, and it will tell you what slot you signed up for. So make sure you show up during your slot. Now, we actually want you to show up a little bit early. We said 30 minutes early if you can. If you have a class right before and you can't show up 30 minutes early, just show up as early as you can to your slot, to gates 5207. And then from gates 5207, we will tell you which room you'll actually be taking the midterm in, because we have a couple rooms reserved. And depending on which ones are full when you show up, we'll assign you to one that has an available seat. Once you get to the room you're actually assigned to, what you'll do is there'll be a proctor in there, one of the TAs will be in there. They'll ask you to show them your student ID. So make sure you have your student ID with you. And then once they confirm that you are indeed scheduled to take it at that time slot, they will give you a password so that you can start your exam. You'll sit down at one of the computers and type in the password they give you, and it'll let you log on to the exam system. So make sure you have your student ID with you. Make sure you show up during your slot so that that can happen. You are allowed to have a note sheet, which can be a double-sided 8.5 by 11 sheet of paper. You cannot put worked out problems on that sheet. So things you can put on it, you can put the formula for how to calculate the value of a floating point number, how to calculate the bias. You could put stuff about how how to calculate caches, how caches work. You can put that. You can put what assembly instructions do if you want those. But you can't just take an example problem and write out the problem in the solution or the problem in the work in the solution on your note sheet. Okay? Does that make sense to everyone? Yeah?
We have code that we use, not for specific, just as a reference, I suppose.
What kind of code?
If we needed a certain, maybe an example of how moving works in assembly or something.
How moving works? Yeah, if you want to write some assembly code, as long as it's not like an actual problem, you can certainly have a move and say it takes the thing in the first operand and moves it to the thing in the second operand. And the operands are allowed to be registers, or the first one is allowed to be a constant or stuff like that. That's allowed. And also there will be no office hours this week. That was also emailed out. All of the stuff on this slide you should have received in an email from Professor O'Halloran also. But there will be no office hours this week. You can email the staff list if you have questions, but do note that with as many students as we have, responses will be slow to the questions on that staff list. So if it's something where you can find out the answer by looking in the book or the slides, you should do that rather than just emailing us, because we'll probably just tell you to look in the book or the slides if that's actually where it is. And don't be doing it 5 minutes before your exam is scheduled, because you probably won't get an answer before you have to take your exam if you're that last minute. So what should you study? You should study chapters 1 through 3 and chapter 6. The exam will not cover anything other than what's in those chapters, but it will potentially cover everything in those chapters. So that is what you should study. To study, one of the things, there's a recommended study method of studying. If you don't know how you want to study for this midterm, try reading the chapter. Maybe try rereading the chapter. Maybe try even reading it a third time. You should work the practice problems in the book. Those will be very helpful. And also, extremely helpful is that we have released previous midterm exams, and doing the problems in those are a good way of knowing if you are ready to do the sort of problem you'll see on your actual midterm. You should note that the online practice exams, the online old exams that we released, do sometimes contain questions that use the IA32 architecture, so that's the 32-bit conventions. We, starting this semester, are only doing 64-bit, the x86-64. So if you see things that are IA32 specific, you don't need to know the IA32 specific parts of those questions. So things you might see are like 32-bit stack discipline, or 32-bit stuff with a base pointer. EBP was used as a special base pointer often. We're not doing that this semester, so you don't need to worry about those particular questions. But anything that's 64-bit from those questions is fair game. You might see similar stuff on this exam. Any questions about that? OK. So a review of some of the things you'll need to know how to do. so bits, bytes, integers, you should know how to do some basic bit operations by hand. If you see a shift of 3 right shift by 1, you should be able to figure out what that will be. You should be able to do bitwise negation. You should be able to add numbers. You should be able to bitwise AND, bitwise OR, bitwise XOR. You should understand how all of those operations work and be able to do them by hand, because you won't be able to actually type in code and run it and figure it out that way. But these things might show up where you would have to do them. You should understand the representations of different numbers. So if you have integers, you should be able to say, given an integer with W bits, what's the biggest signed number you could represent? What's the biggest unsigned number you could represent? What happens when we're casting between the signed and unsigned? You should understand all of those rules and know how to figure those out for any number of bits. You should understand the difference between the logical and the bitwise operators, so the difference between the logical AND of 2 values and the bitwise AND of 2 values. And you should understand all of the casting rules. So if you are doing an operation on 2 things that are of different types, so maybe they're different sizes, or one is unsigned and the other is signed, or maybe they're different sizes and they have different unsigned and signed, you should know what the implicit casting rules are and how the operation proceeds. So any questions about that? And of course, these are all things you can write on your note sheet if you don't want to actually memorize them. So of course, you should also know floating point. You should know how to calculate the sign bit, the exponent, and the mantissa from the bit pattern of a number, given a particular floating point format of how many bits we're using for each. And you should be able to then turn that into what the actual value of that floating point number is. Of course, we're using the same floating point standards that we've been using in the book, with the implicit leading 1 for the normalized numbers, and then the implicit leading 0 for the denormalized numbers. So of course, there's the bias. You remember that. This is calculating the bias for a normalized number. We've got the 3 main categories: the normalized floating point numbers, the large ones that are not near 0, the denormalized, which are the small, evenly spaced ones near 0, and then of course the special values, infinity and not a number. And so, okay, so here's some more stuff about floating point, a little table about the different bit representations and the floating points corresponding to them. So of course, you should remember in the normalized numbers, we've got this implicit leading 1. In the denormalized, we don't have that. We calculate the exponent slightly differently from the bias, depending on if it's normalized or denormalized. And these special values, infinity, not a number, we know we're in one of those if the exponent is all 1s. Then we have one of those special values, and what we do is we check, is the fraction all 0s? If it's all 0s, then it's either plus or minus infinity, depending on the sign bit. If it's anything other than all 0s and the exponent is all 1s, then it's not a number. Okay, so you should be able to, given a bit pattern, figure out what the actual number is, or if it's one of these special cases.
I think that the only thing with floating point that I really have any difficulty with at this point is really understanding the bias. So the numerical representation of the thing is going to have an exponent, and then you subtract off the bias. So if the exponent is 1, then it would be the same thing as denormalized, right? Except you'd have a 1. Okay, that's how they keep the smoothness between the denormalized and normalized. Okay, so you take the exponent minus the bias, whereas denormalized is 1 minus the bias, which will be like negative 128, I think. So basically, if you have E and you add the bias, then you'll get the exponent. But E is always a positive number. Say E was like 1, and you added the bias, that would be like 127. Can't possibly be it. I think what they're saying here is like the exponent is the bit pattern, and you subtract the bias to get the actual exponent. So let me visualize that. So now if we have like exponent bits are 1, say, minus the bias, then it's going to be really low. Okay, that makes more sense. So whatever the bit pattern represents, you subtract off the bias to get the actual exponent. Unless the exponent bits are all zeros, in which case it is 1 minus the bias. That doesn't fully grok with me. Hopefully he covers that, the biasing.
Then you should be able to go the other way too, which, you know, you did this on Data Lab. You actually wrote code for this. So now we're just asking you to do it by hand, potentially for a few numbers. And then, of course, you should also remember the rounding rules, where if we're exactly between two numbers, we have this special rounding case where we round to even. OK, so here's an example floating point question, and we'll come back and do this one if we have time, if there aren't questions from you that you want to do instead. Another topic that might be on the exam is assembly. So you should be able to recognize assembly instructions, the ones we've seen so far in class. You know, we've seen moves, we've seen arithmetic instructions, we've seen things like LEA, we've seen some stack modifying instructions like ret and push and pop. And you should understand all of these instructions, what they do in the machine. You should understand all of the uses of registers in a 64-bit system. So you should understand things like RDI will contain the value of the first argument passed into a function. RSI will contain the value of the second argument. That RAX is going to be where the return value is when you return from a function. You should understand, you know, the difference between the callee saved and the caller saved registers. All of that is stuff that you should know. You should understand how different control flow in a C program gets turned into assembly. So what it looks like when you compile a for loop or a while loop or a do while or an if else or a switch. You should understand all of assembly. You should be very comfortable with the difference between seeing RAX in assembly and RAX in parentheses. Now that's the difference between saying we want to use the value in the register and the value in the register is a memory address that we want to dereference and use the value of that address. And you should be comfortable with that. You should be comfortable with the different ways that we address memory. So, you know, we have all of these fancy patterns where we've got these different you know, offsets and indices and multipliers. And we have, you know, some combination of these. You should understand how all of those work to actually calculate where we're going to dereference in memory. You should understand the difference between Leah and move, all of that stuff. And so then we have, if you don't have questions, we'll go over this assembly loop example in just a moment. Another thing, assembly, you should understand the stack discipline for assembly. So, of course, you only need to know 64-bit stack discipline. This is one of those things where in the old exam questions, you will probably see 32-bit stack discipline questions. The stack discipline was significantly different back then because they didn't pass any of the function arguments in registers. They were all put on the stack. And that made things a lot more complicated and annoying. You don't have to know any of that. Just focus on any 64-bit stack questions you see. That's the convention that you need to know for this exam. Now, you should understand how you return from a function, then gets passed into EAX, and then you have a ret. And, you know, you should understand these different instructions that modify the stack. So calling, returning, pushing, popping. And another thing you might see on the exam, arrays and array accesses. So you should understand how arrays are laid out in memory. So remember that a 2D array is, you know, implemented as a flat 1D sequence of bytes because, of course, our actual memory doesn't have multiple dimensions. And the way we get, you know, something in a different row is we have to, you know, we go by the width as a multiplier to get to wherever the actual value is. So you should understand, you know, how to get the value of a multidimensional array. And of course, you know, this scales. It's the same idea for, you know, 3D or 4D or however many dimension arrays you want. Is that, you know, we have to scale by whatever amount to get into this flat 1D array. Okay, so, you know, something you might see on the exam would be something like this, where we give you some C code that says we're going to do this array operation. Here we're just taking some value in array 1 and assigning it to a location in array 2. And you're given some assembly. And this assembly is, you know, the compiled version of this. And we ask you to find what the actual values of H and J are. So the dimensions of the array based on the assembly that was used to do this assignment. This is something that you should know how to do. And you'll see, you know, this one is from fall 2010. You'll see in the old exam problems examples of these to practice. And we can go over that one.
Pretty sure I did this exercise in the book. It isn't immediately obvious that you could just pick out the sizes because there's no balance checking. And it's just like saying, hey, copy array value at x, y in array 1 and put it into array 2. Like there's no inherent necessity for the sizes to be there. But because there's specific offsets being used, like 4 here, I guess 4 would be the size. So array 1, it's going by the size of the int. But then array 2 is going based on RDIs, is going based on REX. So yeah, you can compute it if you read through this assembly, what those sizes are. I did it as a practice problem. They even give you the calling convention here. So EDI and ESI are X and Y. So EDI gets moved into RDI. So these just get extended into 64 bits. So RDI here gets moved into RAX. No, it's added. Yeah, so this is where we're computing the index. So RAX is going to be the index into array 2. So everything that's RAX involved is an index into array 2. Everything that is RDI involved is indexed into array 1. So array 2, it looks like it's saying, hey, move RSI, which is the X value, into RAX. And then this is, I think, a subtraction. Shift arithmetically left quad word. So that would be multiplying by 2 to the power of 4. So 2 to the power of 4 is going to be 16. So we're multiplying, we're multiplying RAX by 16. That doesn't make sense. RSI, oh, because it's an indice. Okay, so we're saying, hey, multiply, so we're computing y, so this is going to be y times x. So I think this is computing y. And then we subtract off RSI from RAX. Oh, so this is, instead of being 16, it's going to be 15. And then we add RDI to RAX. So it's 15. So I think 15y. I think J is 15. I think that's how we can figure that out. And we just add RDI, which is X, onto that. Okay, that makes sense. And then here, so we haven't touched RDI other than the extended to 64 bits. Here we say RDI, we're going to load up the address at RDI times 2. Oh, sorry, the index RDI. So this is basically multiplying out RDI. So I think J is 15. This is computing H. So RDI times 2 and one more, which would be 3. So this is going to be 3. We're multiplying by 3. And then we add in RSI, which is Y. Yeah, that makes sense. So I think it's 15 and 3. Because RDI goes directly in here, padded 4. Yeah. I think it's like 15 and 3. But I'd have to step through it. More
caching concepts. So you should understand how caches
rigorously.
work. Hopefully you learned that in Cache Lab when you wrote your cache simulator. You should understand, though, the number, how caches are divided up into sets, and each set has the sets have some associativity. The whole cache has an associativity, which is the number of lines per set. That each cache has some particular block size, and how we can calculate the whole size of the set from that, or the size of the whole cache from those numbers, how we can find out where an address is in the cache, if it's a hit, a miss, if we have to evict something. You should understand hit rate, miss rate. You should understand sort of how we can make design decisions in our caches that allow us to avoid particular types of misses and what parameters we would tweak to get that. So that's sort of like, this is the idea of, by changing your associativity, if you change, from a direct map cache where there's only one line per set to a fully associative cache where all of the lines are in one big set, this changes our misses because in the fully associative cache, we only have a miss when the cache is completely full. Or we only have to have an eviction when the cache is completely full and we have a miss. Whereas with the direct map cache, we might have empty space in our cache and still evict things if they're in the same set. Does everyone understand that? Okay. And that you can refer back to the cache lab slides about the the cold miss, the conflict miss, the capacity miss, the different things we had. Okay, so what we're going to do now is for the rest of miss, the conflict
It's
miss.
funny, you just cruised right over that relax
capacity miss.
slide.
The different things we had.
Work past exams? What does that mean?
Okay, so what we're going to do now is for the rest of the recitation, we're just going to go through practice problems. And so I have a couple. I have the couple that are already in here. Actually, before we do that, I just want to one more note is anything in chapters 1 through 3 and chapter 6 is fair game, even if it's not in these slides. These slides are an overview, but they're an incomplete overview of things you might see on the exam. Anything in those chapters might show up on the exam, even if it's not something that I mentioned in these slides. Okay, so just to let you know. But for the rest of the recitation, I just want to go over review problems. So before I go over the sort of the pre-planned ones I have in these slides, are there any particular topics, questions, review problems that any of you would like to go over or see? Yeah.
Kind of if you have struts and you're padding, and you do the padding.
Right.
So if you have a char array, will you ever need padding before that?
So do you ever need padding before a char array? Yeah. So a char array, is just a bunch of chars. And since chars are 1 byte aligned, then it's okay to put them wherever you want. Right. So that one will be okay.
And if you have a struct within a struct, like let's say the struct you have within the size of 6, so it has an hint in the struct,
Okay.
would you still consider it to be like size 6 in the sense of padding, I guess?
So a struct, the struct itself needs to be aligned to the size of its biggest member. So if if the biggest thing in the struct is an int, then the struct itself needs to be aligned to a multiple of 4. Any other questions? Yes? Finding the percentage of hits and misses, okay. Is there a particular example you have? Okay, yes, so can I take this? Okay. Okay, so here's an example problem. This is from one of the old midterms. It's on the website, right? Is that where it's from? Yeah, okay. So this is an old midterm question. Okay, and it's about caches. And so it says that we have a cache with 512 bytes. So the size of C is 512 bytes. Okay. And we know that the cache is LRU. Eviction policy least recently used. That's the one you implemented in your cache simulator. And we know that the cache is initially empty. Okay. So that's our setup. And we say that we send the following addresses to the cache. So we're going to send it 024.8.16.32. We send it 024.8.16.32. Let's see, assume. It doesn't seem to say. This one is fall 2011, exam 1. This is fall 2011, exam 1, problem 8. Okay, it doesn't seem to say what the associativity is. Maybe we don't need that. And okay, so we get the address. These addresses are sent to the cache, and the hit rate is 0.33. So let's see. So we sent 1, 2, 3, 4, 5, 6, and the hit rate is 1/3. So that meant that we had 2 hits and 4 misses. So that's the first thing we figured out. That wasn't given to us. We just figured that out from the hit rate and the number of addresses we sent. That was just a little bit of simple math. Hit rate times the number of accesses is the number of hits, and then, of course, the rest must be misses. And the question is, what is the block size of the cache? Okay, so what is the block size of the cache? Okay. So let's see. So let's see. So we know that see if we can move over to the caching slides while we do this. Okay, so what we know about a cache, so we know that the size of a cache is the number of sets times the associativity times the block size per line, right? So that, sets times associativity is the total number of lines, and each has block size bytes. So we know that 512 is going to have to be equal to the number of sets times the associativity times this block size, okay? And this is what we're trying to solve for. So the block size is going to be equal to 512 divided by the number of sets times the associativity, whatever that ends up being. Okay? And so now we want to figure out what this is, and then we'll have B, okay? So we know that we had 2 hits in this pattern and 4 misses. So what do we do? Cache is initially empty, so it's obvious that this is going to have to be a miss because the cache is cold. We know that one. Okay, and actually we do have some options. We know that our options are either b equals 4, b equals 8, or b equals 16. So our options are b equals 4, b equals 8, b equals 16, or none of the above. Okay, so this is nice that we actually have now only sort of 4 things we have to test out. Does anyone have any ideas on what we could do now to sort of figure out which one of these it is?
0 to 4 are the addresses. Oh, they don't.
These are the addresses, yes. So they're very small addresses. So these are the addresses. Okay. Any ideas on what we could do given the fact that we actually only have 4 options? That would be reasonably quick here. Yeah, we could just say, okay, let's assume it's 4. What are the hits and misses going to be? Let's assume it's 8. Let's assume it's 16, and see which one of them ends up with 2 hits and 4 misses. That actually seems like a reasonable thing to do, because there's only 3 things we're going to have to try out. Not every question is going to be multiple choice, but there might be multiple choice questions on it. An old midterm question, and it happened to be multiple choice. In general, though, this sort of strategy of we've narrowed it down to some set of options, and now we can just test them out is something you can use, even if it's not multiple choice. Say, well, I know it's going to be either this, or this, and I'm not try them out and see which one works. Works even if it's not multiple choice, if you can get it narrowed down to a small set of options. Okay, so let's see, what would b equals 4 do? Okay, so b equals 4. The cache is 512 bytes. Then if b equals 4, then s times e is going to equal what? 512 divided by 128 equals 4, is that right? Yeah, okay. So s times e is 128. So what does that mean? Yeah, definitely, it does not say anywhere what our e is. Yeah, so this is all we know. What?
Yeah, we don't need S anymore.
Oh, yeah, do we not need s? Okay, yeah, we don't even need s.
It would be okay if b equals 4.
Right, yeah,
Or
okay.
miss.
Yeah, with b equals 4. Right.
Miss.
Hit, miss,
Hit.
hit,
Miss.
miss, miss.
Yeah, so that's the opposite.
Okay, so yeah, so that looks like it ended up being 2 hits, 4 misses. Okay, that's good. Okay, right, so what we said was the block size is 2, or the block size is 4 bytes. What's going to be in it? So we miss on 0. That loads up 0, 1, 2, and 3, because it loads up 4 bytes. So 2 is loaded up, so that's going to be a hit. 4 is definitely not loaded up, so that's definitely going to be a miss. See, but is this actually a hit?
Oh, wait.
Right.
No, I think that's
Right, yeah. We loaded up 4, 5, 6, and 7. So then 8 is actually also a miss. 16 is a miss. 32 is a miss. Okay, so this was actually 1 hit, 3 misses. So we were slightly off. Okay.
One hit, 5 misses.
Yeah, 5 misses. I can't count. Right, yeah. So does everyone see why 8 was actually a miss? Our block size is 4, so that means the first block is 0 through 3, and the next one is 4 through 7, and then 8 through 11 is a different block. Okay. So that was, with 4. It was 1 hit, 5 misses. Let's try it with 8, because this obviously didn't work now. We see. So what happens if we have 8? The first one's always going to be a miss because the cache is initially empty, right? Can't possibly be in it. And then that loaded up what? That loaded up 0 through 7, right? So 2 is in there, 4 is in there. Now 8. Is 8 in there? No, because we loaded up 0 through 7. So 8 is a miss. Is 16 in there? No, because when we loaded up 8, that loaded up 8 through 15 because the block size is only 8. So that's a miss. And the same thing here, 32 is not in there. OK, so that gives us 2 hits and 4 misses, which is what we were looking for. So it looks like B is the answer. We could, just to double check, look at 16 and make sure that that comes out to something other than this, so that we can be sure that we actually did get the right answer. If we did 16, let's see, 0 is a miss because the cache starts empty. Then what happens? Well, we loaded up 0 through 15, so we're going to see, OK, all 3 of these hit, and then this is a miss, and then this is a miss, because that loads up 16 through 31, and now 32 is a miss, but that's 3 hits, 3 misses. It looks like the one that gives us our hit rate is indeed B equals 8. So yeah, so there we saw that, OK, we were thinking about like sets times associativity. We didn't actually need that. That's why the problem didn't tell us what the associativity was. It didn't even matter. We didn't need any of this. What we really needed, actually this, the fact that it was 512 bytes isn't even useful. All we care about is that's big enough to hold, 1 block, which it better be. And then we were able to figure it out just by plugging them in and looking at what happened. So that was good. It gave us a little bit of information that wasn't, actually something we needed. We went slightly in the wrong direction at first, but then we realized we could just look at the block size and look at the patterns and use this hit rate to figure out which one of them was the one that matched it. And since there was only 3 to check, that was fast enough. Hopefully you can do that when you have 4 hours. OK, so are there any questions about how we got B from this problem? Yeah?
So it's able to load up the amount based on the block size.
Right, yeah. So every time we have a hit, it loads that whole block into the cache.
And we're kind of assuming like each int is like just one of those. Like the next 4. Let's say your block size is 4, and like each of them following is just fit one of those blocks.
So, well, yeah. So these are actually bytes. So we're saying the block size is 8 bytes, and the addresses we gave it are byte 0, byte 2, byte 4, byte 8. Right. So if these were integers, then the first integer would actually be all of this. So it looks like we're not doing integers because we're getting something at offset 2, which would be halfway through an integer if we were doing integers. Any other questions about this? OK, so there is Fall 2011 problem 8 solved. Are there any other questions? Yeah, OK.
There's a question on Fall 2012.
Fall 2012.
60 question.
This is Fall 2012. Number 6. Yeah, if I could see the question. Okay, so this question is, so this is about structs. Okay, so this is a long one. Okay, so we've got struct confuse with a struct. And in it, we have char systems long theory. We have another struct in it called applications. And in that struct, there's a char array of size 3 called web. And this struct is named database inside our outer struct. And we've got an int pointer called languages and a pointer to another struct to confuse. So that, I guess it's like a linked list of these things. And that one's called math. OK, so this is quite the confusing struct, as its name suggests. There's lots of stuff in it. OK. And then what we have is we have 3 code blocks and 3 pieces of assembly, and we want to match up the code block to the assembly function.
Can you just open it up like that?
Oh, actually, that would probably be faster, if I can find it. Yeah. Actually, let me just give this back. Let's open it up. So this is fall 2012, exam 1, number 6. Okay, so there's the problem on the screen. Okay, this is better. So there's the struct. We just wrote down. And what we have is we have these 3 pieces of C code, and we've got 3 pieces of assembly code, and we just want to match them up. So we want to say which piece of C code belongs to which piece of assembly code. And we know that one of them is each of those. It's not a trick question. But okay, so what does our first piece of C code do? So our first piece of C code is going to take a struct confuse pointer, and it's going to give us back a character pointer. And the way it does that is it's going to return the address of the second element of the array, this array in this struct in here. Okay? And one of these offsets is that offset that does that. So what we really need to figure out here is where in memory these things are being stored, where they are in relation to the beginning of this struct confuse, because we get passed in the pointer, that's the beginning of it, and we need to figure out which one of these is going to be those locations. Okay? Does that make sense to everyone? How are we doing that? Yes? So, okay. So are there any of them, even before we do that, that maybe look like we can sort of get away and maybe not figure out what the actual answer is? Yeah.
B doesn't address all the other 2 moves, so we can basically figure out that B is going to be the one that returns an address.
Right, okay. So it's looking like B returns an address, which bachelor's does that. So we're trying to match up A, B, and C. So it looks like, B returns an address, and of these 3 functions, that's the only one that returns an address. So we're thinking that maybe this one is bachelor's. Okay, and then let's see if we can sort of get guesses for the other 2 the same way, and then we'll go and check them and see if they make sense and where they index to. Well, let's see. So what do the other 2 do? One of them is going to return the value, and the other one actually does a dereference. Okay, so which one of these do you think is the one that does A? One does a dereference and the other doesn't. So do we see in the code something? Masters B A. So okay, so that's dereferencing. This one looks like a dereferences too, though. So maybe. Okay. So this one is moving into a 64-bit register, and this one's moving into a 32-bit register. So let's see. So pointer languages. What's languages? Languages is an int pointer. So when we dereference it, we'll get an int, which is 32 bits, right? So maybe then, since this is putting it in EAX, maybe C is masters is maybe our guess. And then that would mean that this one, which puts in a 64-bit register, returns theory. What's theory? Theory is a long. Okay. Yeah, that would make sense. Okay, so these are our guesses. So this is what we think. I think maybe that these are what it is, just based on the fact that we saw, oh, look, we have address of, we've got dereference, we can look at the different sizes. Was there a question? No? Okay. So these are our guesses, but was there a question over there? These are our guesses. What we'd like to do is actually go and look at,
It would be nice if I could find the midterms. So this is the actual website for the course. Information about midterms and final exams. Okay, so this is a 4-month course. And I'm completing in 2 months, March and April. I guess it makes sense. I'm focusing on it. These other students have other things to deal with. To be written. Autolab, Ed, Canvas. What are these things? These are the things you log into. Okay. Alright, well, I don't see any previous midterms. I am looking for previous year's midterms for the Carnegie Mellon. How do you spell Carnegie Mellon? There you go. Thanks. Oh. Here we go. So they are in the exams section. So if we go back here, bam, 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 bam. Oops, open that up. If we go to the exams section, which is home, exams. Oh no, these don't have them. Okay, so it's a different website. $15,213. I guess they changed the website. Read the chapter 3 times, yeah.
No, we got the right one. for this exam, so why not? Maybe if we were actually taking the exam, we'd put these down and then come back after we finished the rest of it to see that these actually match up. If we're reasonably certain that we got it right based on just that little bit of information, then we'd come back and check once we knew that we had time remaining. So okay, so what do we do? So we're thinking that maybe A is PhD. Okay, so PhD goes to math, and then from math it goes to theory. Okay, so where is math going to be in this? So we sort of need to figure out how this is laid out in memory. So this is, a char is 1 byte. So the size of this is 1 byte. So this is just going to be at an offset of 0 from the start of the struct. Along here, okay, so are we doing, we're doing that along is 8 bytes? Is that what we're assuming? Does it say? Yeah, okay, so I think we're assuming that long is 8 bytes here. So this needs to be aligned to its size within the struct. So if the long is 8 bytes long, then even though we have just a char here, we have to wait until we get to the next multiple of 8 to put this down. So these are offsets from the beginning of the struct. Okay, so then we have a struct applications. And what's the biggest thing in it? The biggest thing in it is just a char array. So it's just got some chars in it, so it can be aligned to wherever. So this was, that's not 8, it's 10. Okay, so this was 8 bytes long starting at 0x8. So that takes us to 0x10 as the start of this struct. And that's, okay, then we've got an int pointer. So an int pointer, we have to align it to another multiple of 8. So this is going to take less than 8 bytes. It's only 3 bytes. We'll have extra space because we need to align this to a multiple of 8. So it's going to be at an offset of 0x18. Do we see how we got that? Yeah?
Why is theory not an offset of 1? Because it would be 1 after systems, right? So like 1 byte and then theory.
So the thing is, each element of the struct needs to be aligned to its size. So if this is 8 bytes, it needs to be aligned to a multiple of 8. And that means if we're not already at a multiple of 8, we just add padding until we get to the next multiple of 8. So what happens is we have this character, and then we have 7 wasted bytes, and then we have the long, and then we have the struct. Okay?
So when we do this kind of question, do we assume that we align those elements without optimization?
Yeah, so you should assume that the compiler didn't rearrange the members of the struct to optimize. Assume they're laid out in the struct in the order that they were given. Because of course, yes, the thing is, if you sort them by size, putting the biggest to smallest of that will optimize the use of space. There's a property they mentioned in class, probably. Okay, and then what's left is another pointer. So what do we get? We get x1. Okay. So 8 more bytes after this pointer. That's a multiple of 8, so that's okay. So then, okay, so we said PhD was probably A. So we did pointer to math to theory. Okay, so we went by an offset of 20. Yeah, that takes us to our struct pointer. And then from there, we went by another offset of 8. So yeah, so that takes us to theory in the other struct. So it looks like we got this one right. Cool. Our guess worked out. Do we see how we got that? Yep.
RDI stores the address, right? So why would we dereference it before adding 0x0?
So what we did is we went to an offset of 20 from RDI. So RDI is the argument to the function, the pointer to the struct.
With the brackets, right?
That gave us a struct pointer.
No, I got that, but I mean RDI itself is an address, right?
Mm-hmm. Yep.
So why would we
We want the value at an offset of 20 from the pointer RDI. We want this value. We want the value of the pointer, not the address of it, because we need to dereference it. Does that make sense? So we get the address of the pointer, and then we dereference an offset of 8 from that to get theory. That gives us PhD. Okay, so now we're double checking that B was bachelor's. Okay, so what did bachelor's do? We got the address of the second byte of database. So what did we do? We went with an offset of 12. So 10 takes us to web 0, and then web 1. So that's web 0. Web 1 would be 1 byte more from that, which would be 11. 1 byte more from that would be web 2 is 12. And that is indeed what we put in. So, and we just got the address of it rather than the value at it because we used Alia. Okay, so that looks good. It looks like we found the address there for bachelor's. And then it better be the case that master's is right at this point. But we can even look and check just to make sure that we got it right. What did we do? We said we want to find languages, and then we want to dereference that pointer. So, okay, so we went to an offset of 18 and got that value. Okay, so the offset of 18 was languages, right? And then we dereference it and put that into EAX. So, as an int star, we dereference it to get an int, put that in EAX and return. So it looks like that is also what we did for masters. So we've double checked. It looks like we got it right. This is the correct order. Everyone see how we got that? Okay, good. This was on my midterm, by the way, when I was in the class. I remember it now. Okay, oh wow, it looks like we're actually out of time. Any other quick questions before we finish? Yeah.
How do you tell what LEA is being used for arithmetic versus for progress?
You sort of have to look at the context. You can't just, it looks, the instruction itself looks the same on just that line. You have to look at the context to see how it's being used. And of course, if you want to try out the other practice problems in the slides, you can try those out. Try out the other exam problems.
Everybody.
So I think I'm gonna go ahead and break here. This will be what, 11:45, something like that. We'll just say 11:30 because we're close to 11:30. I'll pull this up here. Might take a little bit more time, so I don't rush myself. And then this one, I'll bump back 15 minutes here, 1:15. Okay, so what do I want to accomplish when I get back? Let's go ahead and save that. I think it's time to bust out the book again. So we are on, I don't want to take any of the midterms. I don't think that'll be necessary. I wanted to go over their review though, just to see what type of problems they're asking, make sure that I feel confident in answering them. The one thing about floating point representation is that knowing the biases for the different representations and being able to calculate the exponents, I find that to be something that I'm not confident in. So I could probably use with some experimentation there. But otherwise, I feel pretty confident in the stuff that they had in the midterms they went over. So I think getting into the reading again, exceptional control flow is my next next thing that I want to focus on. And that is what, let's see, we got about 40 pages there, and it looks like another 20, so it's about 60 pages, probably a little more than like 63 or something like that of reading. If we look at the contents real quick, exceptions, processes, system call, error handling, process control signals, non-local jumps, tools for manipulating processes, etc. These are all things that like I'm somewhat familiar with already, just from experience and from reading the Linux programming interface. So I think what I'll do is I'll read through this and then I'll be selective in which exercises that I take on, because I only got so much time on this planet. So I don't want to waste time doing problems that are not going to really help my learning. It's kind of crazy. I'm 760 pages into this book, and we're just at the midterm in the course. It's because the course skips a lot. Like 1, 3, and 6 were the chapters that the midterm covered, which is, sorry, 1 through 3 and 6, which is all the machine level representation, bit representation of different data types, tour of computer systems, and they skipped over 4, which is processor architecture, 5, which is performance stuff. And they got straight into memory hierarchy. So we've already done linking. So now we're in exceptional control flow. Cool. All right, I'm going to take a break here then, grab some lunch, and do my cardio, and I'll be back. All right, see you then. Bye.